we started looking at micromechanics and the simplest of that, and you also had a homework based on that, which I think all of you have submitted. So what we did last time was look at the longitudinal modulus, for which we took up a okay. Oh, thanks. So we took up a cross section like this, which is also not exactly realistic, but more realistic than what we actually took up. Instead, we took it up as made out of two parts, like a bimetallic strip. One is the fiber, and this is the matrix. So we will continue with the same model, which helped us get to this particular result. And in doing that, what we had done is, because we were interested in the last class in the longitudinal modulus, so we applied force which was perpendicular to this cross section, a tensile force. We tried to pull it apart on either side, and then we saw what is the behavior of the matrix, what's the behavior of the fiber, what's the behavior of the composite as a whole, if you want to think of it as an equivalent homogeneous material. So that's precisely what kind of strategy we will use, but the loading direction will change now, because now the next thing that we are interested in is so the next thing that we are interested in is ET, which is the tensile modulus, and we will follow the same convention as far as the subscripts are concerned. F refers to the fiber, and M refers to the matrix, and we use V, small v, to refer to volume fractions, and we are considering that only the fiber and the matrix are there. So either one of them, if it is given, the other is not independent. It is one minus the other, so it's directly known. And just to give a possibility of the fiber being anisotropic by itself, we had to mention that it is longitudinal, but in many cases it may not be necessary, just EF might do. So that is one thing. The other thing is, though strictly speaking we should put a C over here to refer to the composite that is made out of this fiber and matrix, we said that where we do not put that subscript, it's understood that it's of the composite. So we will continue to follow the same convention over here, and we will see that unlike this, as well as the homework that you did for the Poisson's ratio in the LT plane, that is the longitudinal transverse plane, as far as the ET is concerned, the behavior is quite different, and instead of what we had over there, we would have something like this, where we would have ET of the fiber, the volume fraction of the fiber, plus the volume fraction of the matrix divided by the Young's modulus of the matrix, so which we are assuming it to be isotropic, and therefore not putting a subscript of L or T on that. So this is very similar to what you would have seen in many programs, whether you're dealing with springs, dashpots, resistors, or inductors, capacitors. In many of these situations, you would see, depending upon whether these elements are either in series or in parallel, you would see that you would either get this kind of a relationship or this kind of a relationship. And that is something similar to what is happening over here, because in this what had happened is that we were applying the force along the direction in the previous class. When we did that, it's very easy to see that if you can think of these two material chunks that you have as springs essentially, and those springs are in parallel. Okay. So this is the stiffness due to the fiber. This is the stiffness due to the other way around, because I put M on top. So this is the matrix and this is the fiber, and essentially you're applying that force, which is the force along the longitudinal direction over there, and you saw that the thing that remained constant here was the displacement, and what added up were the forces. So the total force that you had over there, F, you had to add it up as the F in the fiber, FF, plus Fm, which is the force in the matrix. And then you are able to use those two relationships, one that the displacement is constant, the other that the forces are adding up, in order to arrive at this particular relationship. Now we are going to take the same model. Now instead of applying the forces in the direction what we showed over here, we are going to apply the forces in this particular direction, that is transverse or perpendicular to the longitudinal direction. And once we do that, we will see that this role of the force and the displacement gets reversed. In other words, their forces were getting added up. Here displacements are going to get added up. You can very easily see that when I'm pulling these two apart, this is going to stretch by a certain amount, this is going to stretch by a certain amount, and both of these total stretch is going to be given by the sum of the stretches of both of this. On the other hand, as far as the force is concerned, you can very easily draw the free body diagram of either only F or only M, and you would see that this force has to be resisted at the interface. So whatever force you're applying over here, let's call it F, that same force has to be at the interface as well. So it's very clear that whether it is the matrix or the fiber, it is facing the same force. And then the interface area, whether we are considering the matrix or the fiber, the interface area is one and the same, and force in this case is a normal force, and therefore the stress is also normal stress, and that normal stress is that force divided by area of the interface, and both the forces are same, so the interfaces are the same. So very clearly you see that the stresses are going to be the same. So now that is the main difference between those two cases. Here, because the displacements were the same, the initial lengths were the same, therefore the strains were the same. So this is essentially an resulting from an isostrain assumption, which is reasonably valid, whereas here you are having an isostress assumption, which is not so valid. So this is pretty much valid, because of which the results that you get out of this, even though it's a very, very simple model, are close to what you would get in an experimental test as well. If you were to know all of these values and compare it with the experimental values, you would see that this equation would more or less hold. Or in other words, if you plot that particular equation versus the volume fraction, so in this we will plot all the E's of the composite, whether it is EL or ET, and we see that when the fiber volume fraction is 0 and 1, the two extreme cases, so it will be, when the fiber volume fraction is 0, it would be E of the matrix, and then it would be E of the fiber, either in the longitudinal or the transverse direction, and then you would see that first curve that we had, which is essentially your isostrain, was a straight line. It's a linear equation in VF that you see, because Vm can be written as 1 minus Vf, right? Now, when we come to this particular equation, on the other hand, once again we are plotting that E, instead of EL we are plotting ET, then you would see that this would have a relationship which is there, because of which you would see it is almost a constant. It will be a slight increase. I've probably drawn it in an exaggerated fashion, but essentially the effect of the fiber will not be noted until the volume fractions of the fiber become fairly large. Yeah, volume fraction of the fiber becomes large. So, and we also saw that typically the values of practical interest for us is only between 0.4 to 0.6, so it really doesn't matter what is happening at the extrema, because first of all, you may not be even able to pack, depending upon the fiber geometry, unless it is, let's say, a square or rectangular fiber cross section, you'll not be able to pack it to 100% anyways. So there will be gaps that are there, and since we are assuming that other than the fiber and matrix, there's nothing else, not even voids, so very clear that there will be some matrix or the other. But what is for structures, typically flight vehicle structures, would typically be in this particular range, and that's where you're interested in. Now you get some kind, so this is, let me call this as iso stress, because I'm essentially plotting this particular equation, which is derived on the iso stress that, as we reasoned out, the force is the same, the interface area is the same, and the stress there is normal stress, which is just given by one over the other, and therefore both the numerator and denominator being equal, it's essentially an isostress approximation. So this is what is a little doubtful in nature, because of which this particular equation many a times does not agree one-on-one with the experiments, or it's, in other words, the kind of scatter that you get with that is much lesser compared to the scatter that you get with this particular equation for the transverse direction. So though we will first derive this particular equation today in this particular slide, it is seen that since this is not good enough, these become some kind of limits between which this can happen for typical material properties, though we have taken just the example of EL and ET, and you have done a homework for new LT. Many other properties also are somewhere in between that. In fact, we started off talking about the rule of mixtures with the simplest example that we can of the mass density, and we showed how that is essentially weighted average of those two quantities, material mass density in terms of their volume fractions. So what really happens is that for most materials, if you actually do an experimental test, it's somewhere in between these two is what you see, especially for these kinds of values. EL would pretty much be on this, but your ET would actually have some effect of the fiber even in that range that we are interested in. There's a small contribution from the fiber that is happening over there. Now, why is this isostress not as valid as an isostrain approximation? Is essentially because of the crude model that we are getting into. We can very easily see that if I'm actually applying a stress on this or a force on this in the transverse direction, the way it will be getting distributed is very different from what this simplistic model suggests to us. Nonetheless, because these are going to give us limits, what we typically call as the Voigt limit and the Ruiz limit, VOIGT and REUSS. These are a little more involved things, but essentially it's in terms of upper limits and lower limits. So from that perspective, I'm mentioning, because these are very commonly used in the literature, and you might come across this, especially when you're referring for the homework you would have already referred. We would have a very similar homework based on this particular model that we are going to derive today, an equivalent of that as far as the shear modulus is concerned. So now, so this is what, if you do experiments, you would typically find values which are going to be like this, and when you join them, discrete values, you do a curve fitting essentially, you would end up with somewhere in between these two, closer to the isostress. It's just that this is an approximation, but not a good enough approximation. So that is the reason why it falls close to that. So now let's go ahead and apply this force. We know that the stresses are equal in the composite as well as the fiber and the matrix. And this stress in turn is going to be given by the modulus times the so the modulus that we are interested in here is ET times the area that is being exposed to that. So that area that is being exposed to that is the same in both these cases. So we would just talk about, I'm sorry, what am I doing? Yeah. So this is first into the strain. So So you would have, yeah, let me be consistent and use the strain that we will be using with this, which is your gamma TT, that strain that you have in the composite. So when I don't put C, it's understood that it is the composite. Whereas these things are going to be given by your E of the fiber. Again, the fiber could be anisotropic, so we put it as ETF, and it is the gamma TT in the fiber. And this is your Young's modulus of the matrix, which is assumed to be isotropic, and you have your gamma, which is the TT in the matrix, right? So this is what you have as far as the isostress is concerned. But now we also know that the displacements are getting added up over here. So that displacements are getting added means that you can think of the amount which this M expands. Let's say it's initially Tm, and this thickness is Tf. And after the force is applied, this becomes Tm plus, let's say, a delta M, and this becomes Tf plus a delta F. Okay. Now, that strain is going to be given by that change in length divided by its original length, which in this case is the thickness direction. So you would have delta M by Tm as the strain that is coming due to one of them, and the other one. So first of all, let's write delta for the composite is equal to delta for the fiber plus the delta for the matrix, all in the thickness direction. And this delta, we can write it in terms of the strain times the total thickness. So in this case, it is gamma TT, which is for the composite, times the overall thickness, which is Tm plus Tf, which we will call as T over here. So this is T is equal to your gamma TT in the fiber multiplied by its thickness, which is Tf, plus gamma Tt in the matrix plus its thickness, which is Tm. Now, we can divide both sides by T. So when we divide by T, this cancels out, and Tf by T, because the area is the same, becomes the volume fraction of the fiber. So in other words, you can multiply the numerator and denominator both by the length and the width, and therefore you can see that there are essentially volumes of fiber, volume of composite. So that ratio is what we have been defining as Vf, and this ratio is what we have been defining as Vm. Okay. So now once we have this, now you substitute for your gamma in terms of your sigma by E, and you'll see all the sigmas are the same. The sigmas will get cancelled. So all that this becomes is this particular equation over here. So it's very direct and straightforward once you have made this particular approximation or assumption. So the question is really where how valid is that? That's the only question, and experiments show that it's not exactly valid, but it's round about the same if you want a very, very crude first approximation, which is simple enough to derive for you. So are there any doubts in this particular derivation? I think it's clear. So we'll get rid of this. Yeah. So let's continue what we were doing. Previous class, you had this particular assignment, which was very similar to the longitudinal modulus, your longitudinal transverse Poisson's ratio. Now, very similar to what we have derived now, with the same thing, that reciprocal thing, you can take its reciprocal once again. You would see that the right-hand side reduces to this. It's quite straightforward. So it becomes the product of those two components, transverse moduli, divided by the sum of their, along with the volume fraction, with the reversal in that. So Em times Vf and ETF times VM. So this is quite straightforward to derive using those fractions. Now, the same kind of modeling technique I would like you to do in the homework 4.2, where you would be deriving the shear moduli of the composite in the longitudinal transverse plane, that is in the plane where there is a fiber along the length, and therefore when you're trying to change its, let's say you have an element which is a rectangular element, so at each corner you would have a 90-degree, so you're trying to shear that off. And when you're trying to shear that off, you're essentially trying to change its angle from 90-degree to a different value. And that change is what we call as the shear strain. Of course, there are two ways in which you define the shear strain. The engineering shear strain, which is double of the tensorial strain. So what gamma that we have been talking about over here is essentially the tensorial strain. That's why wherever we want to write the engineering strain, we typically write it as twice that particular gamma. So whatever gamma ij it might be, it's 2 times gamma ij that we try to put over there. Now, so as far as this is concerned, so in other words, the model is very similar. It's just that the kind of load that you're going to apply. In one case, we applied an axial load parallel to the fiber. In other case, today, we applied transverse tensile load. Here, you'll be applying a shear load. That is the only difference. And you'll look at the change in angle that is happening and the ratio of those two, the shear stress to the shear strain, you'll be taking as G and essentially ending up with this particular relationship. Now, just as in the previous example, the more important point for me is this is anyway going to be there in many different sources, both online as well as in many textbooks. So, what is important is for you to understand the procedure, and more than that is the assumption made at each step of that procedure to see based on what ideas or what assumptions, approximations you're trying to go from one step to the other, and how valid that is, what could be the issues associated with it. So let me tell you upfront, just like the fact that ET, GLT also does not agree from this particular equation, if you calculate, does not agree very well with the experiments, and therefore you need to look at ways of modifying that, and many of them are typically empirical in nature. So there are many, many models. In fact, as I said, there used to be one separate course on micromechanics in this department till very recently. And so you'll be looking at various different models over there. But what we are going to just be doing is skimming across just a sample, 1 or 2 examples of such models, which are slightly better than what we looked at. We already said that EL model is reasonably good. What we need to worry about is the ET or GLT that you're going to derive. And for that, I do not want you to get into all of these more refined models. This is just to be aware of the fact that they exist. And many people use this particular model. The Halpin-Tsai model is very, very popular in the literature. I've written in a simplified form, taking out a lot of other factors that it depends upon, typically the geometry of the fiber, the geometry of the packing, etc. All of that come into picture. So for the typical case where we have tight packing and we have the fiber as a circular cross section, you would see that that same ET that we derived in the last slide has a slight modification that comes up over here with 2 factors coming in. One is the L by D factor, which is the length to diameter of the fiber. So we are talking of continuous fibers over here. For example, these kinds of relationships are valid for not only continuous fiber composites, but also particulate composites, where you would have particles, typically, let's say, spherical particles, in which case L by D would be equal to 1, the length to diameter ratio. But in the continuous fibers that we've been discussing, we know that L by D is large compared to unity. It could be 10, could be of the order of 15, 20, depending upon the specific kind of manufacturing process used. For example, in filament winding, it tends to infinity. So it's so large because the diameter is of the order of a few microns, and the length could be much more than that. And we also talked about whiskers, which are very high performance fibers, but they are available only in short length. So their L by D will not be that large compared to continuous fibers. So one aspect is that L by D. The other aspect is the factor beta that you see over here. That is essentially a measure of the heterogeneity of the composites. In other words, if you had, even if you had two materials in a mixture, but they had similar properties or either identical or very close to each other, it would not make too much of a difference in terms of what the mixture could offer you. So the fact that one of them is very, very different in its behavior from the other is what makes it so very effective, because you're trying to take the advantages of both sides. So that's for the various different types of applications. So that being the case, there are many ways in which this heterogeneity can be measured. In other words, the difference between the property of the fiber and the property of the corresponding property of the matrix, how different are they from each other? In fact, one of the previous classes, we plotted that EF by EM, and we showed that it goes all the way up to 14 and things like that. So there are cases where it could be even more. So that range is what is important, whereas when you go for metal matrix composites, we saw a few examples of that, the ratio might not be that large. So that beta plays a very important role, and that beta is given by this. For example, if they were very close to each other, let's say the singular case where they are equal to each other, you can see that beta equal to 0, because this numerator will go to 0. And therefore, if beta equal to 0, the denominator will become 1 in this particular equation, and beta equal to 0, this will just become ET equal to EM, which is understandable what we have, because both the properties are identical, the fiber and the matrix are having the same modulus, so obviously ET has to be equal to EM in that limit. And as the difference between these two grow up, so your beta becomes larger and larger. So that's essentially what you're trying to see, what happens when beta becomes larger. So there are lots of sensitivity plots people do versus this, and then they tailor the kind of materials that you can come up with, both for the fiber and the matrix, and see how you can bring in a certain required ratio of these two material properties or difference between these material properties. This can be written in another way, where you can essentially divide both the numerator and the denominator by EM, and then you would see that there's a fraction of ETF by EM in the numerator. There's also a fraction of ETF by EM in the denominator. So this will go. So you can think of it as just two ratios. One is an L by D ratio, the other is an ETF by EM ratio. And those are the quantities that this is going to depend upon. And you can see in a special case, you can also see that you can rederive what we derived in the previous slide for the assumption of isostress. Then you can see that can also be obtained in the limit. Now, the same thing can be extended. Halpin Psi, in fact, is a whole book by itself in terms of the kind of contributions that they have made towards micromechanics. So I'm just extracting two very simple results which are in line with what we derived in the previous slide. The second result being GLT that you are going to do as part of your homework. So there, the relationship is going to be slightly different, but the kind of behavior is going to be very similar in terms of how the two material properties of the fiber and the matrix are going to affect each other. The L by D doesn't have a very big impact on this, but it does. I'm just left it out in terms of the actual factors to keep this equation simple and manageable just for this class, because none of these are going to be things that you're going to be tested for either in assignments or exams. It's just to purely for awareness, just for you to know that there is something more superior to the rule of mixtures that we are learning over here. Another very simple example, just to bring in a different kind of correction from heterogeneity and the fiber geometry is the fact that you have a non-zero Poisson's ratio for the matrix, and that can affect how the transverse behavior is there. So in other words, instead of using the Young's modulus of the matrix to calculate this is exactly the equation that we derived in the previous slide, just that we are replacing EM by EM prime, and that EM prime is not different from EM except for the fact that it's going to be amplified by the factor of 1 minus the Poisson's ratio of the matrix squared. So this is a factor by which EM is increased. And you also saw that curve that I plotted. We had the upper limit, we had the lower limit, and we saw that what this equation was, we derived that in the previous slide, was the lower limit. And the reality or the experimental test that we get is slightly above that. And that slightly above is pointed out by Brintrop for many combinations of fiber and matrix to be essentially coming from this, which is why it is getting a lift up by a certain small factor, and which again joins at the two ends, but in between it is raised up by this particular factor. So that's all that we will look at in terms of refined models. There are many more, as I said. Now we are going to go to homework 4.3, another simple homework, but before we get to that, we need to understand what we are trying to get over there. Earlier, we have looked at each one of these fiber materials by themselves, and it looked really huge advantage replacing them with replacing metals with them. But then we said that, hold on, yes, we are going to have a huge advantage, but not as huge as this, because right now at that point of time we were considering only the fiber alone, which you cannot in reality. You have to bring in the matrix, either polymer matrix like epoxy or a metal matrix like aluminum or a ceramic matrix, etc. So once you bring that, there is a drop that happens, obviously, because the matrix has inferior properties. And this is essentially from your textbook, so it's about 16 years old data, probably even older, because I don't know when they sourced it from. So about 2-decade-old data that you have. And these are all the different specific carbon fibers, the boron, glass, and aramid fibers that we also looked at. But at that point of time, we were only looking at fiber alone. Now we are looking at it with the matrix, and these are the Young's moduli that you have, and the ultimate tensile strength that you have along the fiber direction, and the mass densities of the composite, which is the fiber and the matrix put together. Now, using this data, E and rho, you can calculate the specific stiffness or the square root of that. To in the dynamics problem, we saw that is more important, and in the specific strength as well as sigma u by rho, which is what you have over here. And in SI units, when you use gigapascals, where giga is of course 10 power 9, and then you use this gram per cc, which is in kg per meter cube, it becomes a factor of 1000. So once you put all that together, the typical unit in which this specific stiffness without the square root is typically used is 10 power 6. It's a million meter squared per second squared, and because E and sigma u are both stresses, both in pascals, so therefore they have a very similar unit, meter per second squared. But typically the factors, the strengths are much smaller typically compared to the modulus, which is why the failure strain is typically of the order of 1% or so. So in the brittle composites in particular. So therefore you can calculate these values as well. So at that point of time, you're looking at something like an E by rho value of, with this set of units, about 114, as doing very, very well. But today you have much more superior composites, even from the same manufacturers, and I want you to explore what are the best available today that you can look for in terms of your E by rhos and sigma u by rhos, because it's always good to have these in at the back of your mind in terms of what kind of design choices are available for you in terms of the materials that you can actually use for a particular component that you're designing for a flight vehicle. So these are all longitudinal properties of composites, of course. So just summarizing, these are the three design parameters that we typically use. So in the previous slide I showed E by rho, but what we really use, because most of our flight vehicle structures are dynamically loaded, is this particular quantity that we derived for the natural frequency. We utilized it in a particular way for a particular problem, and then we showed that this is the material parameter of interest to us. So instead of meter squared per second squared, now it becomes meter per second, and you retain that 10 power 3 over there. So as common between these two. And in this case, of course, it remains meter squared per second squared because there's no square root involved. So these are the three material parameters of interest to us. In some way taking into account how heavy these materials are, so that the weight comes into picture, and it's most evident in the buckling or stiffness stability based design. Now this is the homework that you will have. I'll of course put a screenshot of this particular slide on Microsoft Teams, as I usually do. So I want you to find the top 5 fibers that you can find in your literature search, either on the internet or in books, etc., which result in composites along with the epoxy matrix in all cases. So keeping that as the constant denominator for everything, so that you have only change is the fiber that you're dealing with. But obviously you have to choose those fibers which are gelling well with the epoxy. You can't choose any arbitrary fiber which may or may not be compatible with epoxy in terms of chemical compatibility or otherwise, other kinds of possibilities that can exist between them, like the electro corrosion that we talked about, electrochemical corrosion, etc. So another thing I want you to keep a constant for all the 5 is the volume fraction of the matrix, 0.4, and therefore the fiber volume fraction of about 60%, which is typically amongst the more high performance flight vehicle structural components. That's what you typically will use. And I want you to find with maximum values for each one of these 3 material performance indices. It could happen that the 5 that you find for this are not exactly the same 5 that you have for this. There might be overlap. 1 or 2 might spill over to the others as well. But for each, I essentially want you to find 5 each, so that you are aware of which are, in some cases where you might have strength and stiffness of equal importance in a particular design, then you can choose from that basket that you have, which is an intersection of those 2 sets of 5 that you might have, may or may not. Okay, so then buckling, of course, which will show you the typically will lead you to some of the lightest fibers available as per today's state of the art, because of the huge factor of rho that is involved in the denominator over here. So with the 5 that you choose here, 5 here and 5 here, may not add up to 15 because there could be overlap. Some might be repeating. So I don't know how many exactly you might get, maximum of 15. So for each one of those chosen fibers, as I said, ensure its compatibility with the epoxy matrix. And again, epoxy matrices are a huge bunch of family by themselves, and their properties also varies from one to the other. So let's not keep that as a variable over here. So we will use, for all the cases, the Young's modulus of the matrix, assume it of course to be isotropic, which epoxy is, and it's 3.4 gigapascals, and then the Poisson's ratio for the matrix is 0.3, and then your mass density is 1,200 kg per meter cube. It's essentially slightly heavier than water, so it would sink in water, just the polymer alone. And then I want you to repeat this whole exercise with metal matrix composites, because there's a huge trend in the aerospace industry today, especially for propulsion applications, to move from polymer matrices to this. Even in polymer matrices, actually, there's quite a bit of movement, as we already discussed, from the thermoset kind of matrix like epoxy to a thermoplastic kind of a matrix like PEEK, etc. But here we will stick to that epoxy. And here also, for higher and higher temperature applications, obviously again aluminum will not be good enough, you'll need a titanium matrix, etc. But we will just stick to this conventional thing, which many people do experiments with even at academic institutions around the world and including in our country. So for this a standard value which you know for aluminum alloys around 71 gigapascals is what we'll use for the Young's modulus. The Poisson's ratio again 0.3, same as for the epoxy, and the density is slightly higher, 2,700 kg per meter cube. So as always, it's important, I think the teaching assistants have also reinforced this aspect on you. Very important to cite the references, not just dump them all at the end, but wherever you are invoking a particular property, you have to give that specific reference over there. You can give the details of that reference at the end, but where it is invoked at that particular point, you have to cite that particular reference. So that's a good practice that you will develop as you go forward writing your master's thesis as well as your research papers if you publish either conferences or journals. So are there any doubts on this homework 4.3? Okay. So let's get going to the next topic where we will, yeah.
For a composite, like we derive their strengths E and mu, but how do we derive sigma?
How do we derive? Very, very good question. Yeah. So glad you pointed that out. I should have mentioned. The strengths are always a little more difficult to get, okay, in the same direction. For example, if talking of the longitudinal direction modulus, to get the longitudinal strength is also a little more challenging compared to getting the longitudinal modulus. And similarly, the difficulty goes up when you're going to the typical other directions or shear or Poisson's ratios and things like that. So in all those cases, mostly you try to do as many experiments as possible to get these properties. Even for the single material, typically, most of these strength properties are still not very well understood from a physics or a phenomenological point of view. There are exceptions, but mostly you typically do experiments in order to get that, and you do a very large number of experiments to take care of the statistical issues involved, the scatter, etc. So that's typically how you would approach it. Now, for example, let's take the simple example of what we considered in the derivation today. We talked about the transverse modulus, right? So if you are interested in the transverse strength, so that transverse strength, you will see that in reality, it's typically as a thumb rule, it is taken as half the strength of the matrix. So the fiber doesn't even play any role, and you don't even get the full strength of the matrix. Just about half the strength of the matrix is all that you'd get, because you can very easily see if you have just the matrix alone, there is some kind of an integrity to it. Now I'm poking it with so many of fibers, essentially creating some kind of discontinuities over there. That is going to make the matrix performance in the limit, because we remember strength means that you're taking it all the way up to failure, which means there's going to be a crack, the crack is going to grow, etc. So all of that is going to be affected by the fact that there are certain inclusions there in the matrix which was otherwise not there. So that is going to reduce it quite drastically. So one is, of course, experiments. Then there are these kinds of thumb rules that I talked about, the transverse direction, etc. For longitudinal direction, to a large extent, you can take the same kind of a rule of mixtures, the linear rule that we talked about. To some extent, it is valid, but to what strain that can go is very important, because you see that the fiber you might be using could be a very flexible fiber, a ductile fiber, but the matrix could be brittle. So once the matrix fails, all of the load has to be taken by the fiber, and bending, for example, cannot be taken properly and things like that. So you have to do it on a case-by-case basis to see what kind of applications are there, what kind of dominant loads are there, and based on that, you have a combination of these experimental results, either your own or from the literature or from the manufacturers. Many times they supply it to you, and or these empirical kind of rules. Other than thumb rules, there are many empirical rules, like the Brintrup and the Halpern-Tsai that we looked at. That was for the moduli. But similar kind of things exist for strengths also. So you can see that some of those can be utilized as well, but nonetheless, it's a very challenging subject. So if you want to really understand from its depth, you have to go to the phenomenological model. So in other words, the physics of the deformation. So how the deformation progresses. Once the deformation progresses, the damage initiates. what kind of damage initiation might be there, and how that damage grows, and it might be either as the same damage or as a different kind of damage, like fiber breaking, fiber microbuckling, depending upon whether there is compression. Then you could have the matrix cracking, the fiber matrix debonding, the delamination between layers, and how all of these can lead one from one to the other. So all of this has to be understood at its own length scales. Like right now we are doing mesomechanics, is what we will get into next. What we were doing is micromechanics. So in micromechanics itself, there could be different length scales associated with different damage mechanisms. For example, if you're looking at delaminations, typically the length scale of interest to us is the thickness of each layer or ply. Okay, so whereas if you're looking at fiber matrix debonding, for example, it's of the fiber diameter. So the physics that you derive typically cannot be exact, because exact solutions are very, very difficult to achieve there. So you would have to do what is known as an asymptotically correct approach, which means that you're going to drop off certain higher order terms. How do you know which are higher order terms? Based on these small parameters, based on these characteristic lengths. So the characteristic length, depending upon the type of damage you're focusing up yourself on, because that is going to be, you know from experiments that you would have done an NDE based on those visualizations that you have had, the data, you know that certain types of damage is what a particular kind of specimen is more prone to. So then you will try to see if you can understand the physics of that damage, go to the length scale, characteristic length scale of that, drop off all higher order terms corresponding to that, and then you deal with just the leading order terms. Equations become much more manageable, either for analytical results or semi-analytical results, or at the least numerical results, and then you can use that as a database from which you continue with your design. Does that answer you?
Yeah. So generally, sigma will be lower than individual.
Exactly, yeah. So what would be of most interest to you is the longitudinal direction strength, and that you can use the same formula, but make sure that you are not stretching its limit beyond the strain, failure strain of the matrix. Because even though the fiber might have a larger failure strain, the matrix would have already given up, and therefore there's no point in exploring that. So with certain ifs and buts, you have to ensure that you use similar kind of models. But the Halpin and Tsai work that I referred to, they have quite a bit of contributions towards strength also. Okay, those have been refined, because Halpin Tsai's work is almost a half a century old. So it's been around for quite a while, and there have been many others who have worked on it and refined it, but nothing in terms of a big breakthrough like what they brought about so long back. Yeah, so anybody else, any questions? Okay, so let's get on to the next topic. We are just going up one length scale in the upward direction, larger sizes, where we are dealing with the plies rather than with the fiber and matrix that we were dealing with to get the equivalent homogenized properties in the previous thing. And here what is most important, even before we go for the derivations, is to understand the assumptions involved, because many of these assumptions are not peculiar to mesomechanics alone, but they carry over to your macromechanics of the laminate and the macromechanics of the component, the macromechanics of the flight vehicle itself. There are cases where Airbus and Boeing have done either an entire wing or even an entire aircraft analysis just to see how it goes. And such kind of situations, you definitely need to see where your assumptions have been made initially, how valid they are, because at the end of such a humongous effort, if it's just trash that you're getting, there's no point in doing that. So how valid these assumptions are is very important. Validity, we will look at it from 2 points of view. One is in terms of how relevant are those, which is what we looked at, for example, in the isostress versus isostrain assumption. But relevance is one aspect. What has happened is we have inherited a legacy theories, a legacy of results of people who have worked on these kinds of problems in the past. And those things, many of them have made certain assumptions which we can derive even without making those assumptions. In other words, this exact same result can be derived without even making those assumptions. It was under a fallacy that that assumption is necessary to do that. It can be shown that in many examples that you do not need that assumption. You would still end up, of course, a different procedure, but the final results or even some of the intermediate results would be the same. So one is in terms of validity, the other is in terms of the necessity of that. Okay, so relevance as well as necessity. So this is what we will try to answer. As always, whenever we try to learn something very, very significant or important, we try to ask a few questions, because that's what is going to lead us to understanding that subject a little more. So the question we're going to ask here is how, and how the composites are modeled. In fact, with composites, we'll ask many other questions already: why, where, what, etc. So similarly, now we are getting deeper and deeper into the modeling aspects, so which means the how aspects is becoming important. And like any modeling, it means that you need to make assumptions, because that's why it's a model. It's different from reality. Now, these are the two aspects that I brought to your attention. One is to check for the necessity. Can you do away with it and still get reasonably good results, or even the same results for that matter? Or the other is in terms of how valid they are for eventual applications that you're going to take it forward to in the actual flight vehicle. Are all of those assumptions valid? Because even if some of them are and even one of them is not, maybe your result is in question. So each and every one of the assumptions that you make is relevant, which is why I repeatedly stress in your homeworks also to bring up those assumptions, not as a separate thing right at the beginning, just like references right at the end, but at the location where you're invoking those assumptions, so that you understand what is the effect of that. Why is it being used, and how is it simplifying, and is it at all necessary? How valid is it for the eventual application that I have in mind? It may be valid for a narrow class of problems, fine, but is it valid for what I am interested in applying it for? So that's always should be something, a check that you ought to do in the back of your mind. And that of course holds for all engineering problems, not just structural mechanics. So the first thing that we would look at, and we have seen this before as well, is that the materials that we're going to deal with is elastic and valid for small strains that are associated with them. Once the strains go beyond a certain value, what we call as the inelastic limit, we have to take the inelastic model, whatever that is, be elasticity or elastoplasticity or something else, viscoplasticity, etc. But luckily for us, the way we apply either the metals, metallic alloys, the polymer composites, or the metal matrix composites, many of them are within this elastic limit in the typical day-to-day performance of most flight vehicles, unless you're dealing with extreme cases of accident or some damage that has occurred where a component has to be replaced, etc. There you do need to relax this particular assumption. And I'll be using a color code in this list where I'll use green fonts to refer to something that is reasonably valid for a lot of applications that we're going to do, and a whole large class of problems of healthy aircrafts can be analyzed and or designed just by using these kinds of assumptions. Whereas we will go into red zone, red fonts, where we'll see that there's a danger of using those assumptions. Can we use a better assumption, or can we do away with that assumption completely and still be able to produce results? And in between, there are some hazy ones, typically yellow, where you're looking at, or amber, where you're looking at, in some cases it is applicable, some cases it's not. So be very, very judicious about when you want to use those assumptions. So elastic material, we saw many different, I got inputs from many of you during a previous class as well. And after that discussion, we saw that from a mathematical point of view, what this essentially means is that you're writing your sigma ij as a function sigma ij of the strain gamma KL. Okay. So in strict tensorial notation, you would use covariants, contravariants, etc., superscripts, subscripts, and changes like that. We will avoid all of that in today's discussion to keep things simple, not bring in too much of the mathematical complexity unnecessarily. Just to show off. So what we want to do is to understand what is happening in terms of the assumption and how valid it is. So what this means is that each and every one of those stress components, which of course I and J, it's a three-dimensional space that we are dealing with, and therefore we are having 1, 2, and 3. And so there are 3 into 3. 9 quantities that you're dealing with over there, right? So, and therefore 9 functions that you're dealing with over here, and each one of them in general can depend on any one of these 9 strain components, because there's no repetition that you see over here. There's something called the Einstein's summation convention, where any index which is repeated just twice is summed over its entire range. That is not the case over here. Here you have all the variables on the right hand side are different variables that you see over there. So your K and L also go on and take these values 1, 2, 3. And in fact, in the rest of the course and the few remaining classes that we will have, we will follow this convention that whenever I use Latin indices like I, J, K, L, M, N, P, etc., all of them will typically go through the three-dimensional space. And if I use, let's say, an alpha or beta, essentially Greek letters, those will go through only the range 1 and 2. They will not go through 3. Why this is important is that many cases we are going to, as we saw in flight vehicles, we have beam-like or shell-like structures where one dimension is either large or too small compared to the others, and therefore you can end up with a two-dimensional problem, either the cross-sectional analysis of a beam or the reference surface analysis of a plate or a shell. So in either case, we will be dealing with models which involve only 2 spatial variables, that is 1 and 2, and that is something that we will use at that point of time. Now, what this is essentially telling us is many of those qualities that you actually mentioned for an elastic material, the loading and the unloading should be on the same path. It's very clear this particular equation is immune to whether I'm on the loading path or the unloading path. As long as I know the current strain state, I can determine uniquely the stress state. In other words, there's a 1:1 mapping between them, and it depends only on it depends on the strain and only on the strain. It doesn't depend on the strain rate and many other things, which are all important when you go for impact mechanics and even high frequency dynamic problems. As far as statics and low frequency dynamics are concerned, and when do you call a frequency as low or high, it all depends upon certain non-dimensionalization that we do with respect to various factors. We'll not bring all those complications into it, but we will know for a kind of analysis what is low and what is high, and based on that, for typical low frequency problems, high wavelength problems, you will be quite good with this. The strain rates will not affect it. And any other historical aspects of what the material has been through, like for example creep, it can have gone through, it could have gone through corrosion, many other things that could have been there, all could come in as a time history or some kind of modification to this. But right now we are saying that given the strain state, I can get the stress state uniquely. So that's what your elastic material means. So the second thing that we'll be looking at is material linearity. So this is already in yellow, so which means that there are quite a few materials that might be used. For example, rubber is used in quite a few places. For example, your tires, for example, or in certain damping structures, etc. So there could be hyperelastic behavior, and many of that can go, your stress strain behavior can be nonlinear. And in fact, the equation that we just wrote in the previous previous assumption case, was something that could take care of that. You had sigma ij is equal to sigma ij of gamma kl. The reason why I'm not using epsilon, which is typically used for strain, is that we will be using it for two-dimensional strains. To distinguish it from three-dimensional strains, I'm using that. What do I mean by a three-dimensional strain? I mean that it depends on all three spatial directions in general. It depends on, let's say, if you have an x1, x2, x3 coordinate, in general, gamma can depend on x1, x2, x3, right? And of course, in a dynamics problem, time as well. Now, this particular relation accounted for the fact that this sigma ij can be any arbitrary function, which means it could be a nonlinear function of gamma kl also. Now, we are making it slightly even more simpler by saying that there is material linearity. So it all depends upon which flight vehicle structural component you're dealing with, what are the materials being used there, and what is the typical stress strain curve that you have for a particular stress component, some sigma ij plotted with some gamma kl. Usually you're interested in the like thing, that is gamma 11 versus sigma 11, etc. But typically, how does that behavior look like? So if the material is such that even in the initial stages it's not a straight line, even for one of those combinations that you have. Remember, there are 9 of these in general, so you have total of 81, and even if one of them is not a straight line when you plot, then essentially you're dealing with a case where you have material nonlinearity, and you'll have to account for that portion of your work, at least the material nonlinearity, so that you have more realistic agreement with what you observe in reality. But what we are saying by material linearity is that this particular thing is a straight line. So that is essentially what we are dealing with, at least up to the strain of interest to us. So this is, let's say, some particular gamma max, and we know that our structures are not going to be loaded beyond this particular gamma max. I don't care what happens beyond that. So it could be nonlinear beyond that, but as long as with the typical day-to-day kind of maneuvers and the cruise, the landing, takeoff, climb, descent, etc., all those kinds of situations, if the component of my interest is within this linear limit, then this is valid. So that's why it's in yellow rather than red. So that is material linearity. So what this brings us is that that same relation now is written in a specific sense, that it is, let's say, some stiffness that you have, C ijkl into gamma kl. Okay. So now what has been included over here, in addition to the free indices or the dummy indices that we saw in the previous thing, which is also there here in terms of your ij, but now you have these two guys, k and l, are repeating. In other words, there has to be an implied summation over both k and l equal to 1 to 3. So in other words, even though I'm writing it like this, in reality I should, strictly speaking, mathematically I should write k is equal to 1 to 3, L is equal to 1 to 3, and I have to prefix this C with that. So in other words, I have to take that product and the sum of that. But the very fact that k is repeating means that there is a summation over k. Very fact that L is repeating means that there is a summation over L. And both of these being Latin indices, they have variation over this three-dimensional space, that is 1, 2, and 3, and therefore the summation is over 1, 2, 3. So in all future things, we will drop off this saying that it is understood. So once the repetition is there, that is understood. So that's what you're having. So it's also important to state specifically that your C's are constants now. So C doesn't vary with your gamma. So as the strain increases, your C remains constant. Now there is a way in which certain nonlinear problems can be portrayed approximately linearly or even piecewise linearly, where you know for a certain range C is a particular value, one particular C, let's say 1, 2, 1, 1. So that particular C is a constant of a particular value up to a particular value of the strain, and then it becomes a different value. So you can introduce material nonlinearity in some ingenious ways, because it may not be a problem that is omnipresent. It's not there in every part of your problem. It's there on only certain aspects of your problem. So you have what is known as a nonlinear domain decomposition. NDD is a very, very important mathematical technique where you do the domain that you are interested in, you decompose that domain. In other words, divide it into subdomains. There are many subdomains where a linear model will be valid, and there will be a few models, a few parts where the nonlinearity will be very important. So you want to see how you can interface that nonlinear part of the subdomain to the linear parts of the subdomain. Again, nonlinear domain decomposition is a very big subject area by itself. One is in terms of dividing your domain into multiple parts, some linear and some nonlinear. It could be also in terms of your overall mathematical model. There is a certain part of your mathematical model which is linear, certain part which is nonlinear. And we shall see that very soon when we are going to deal with most aerospace structural components. You will see that the displacements and rotations are large, but the strains are small, because of the direction in which you are going to take the derivative will be also large. For example, this is a beam. Now in this beam, this length direction is large, so I might have, let's say, a deflection which is very large. I can also have a rotation, a cross-sectional rotation which is very large. But the way it contributes to the leading strains, the largest strains, is such that there is a derivative with respect to x1 or the length coordinate that is involved. And x1 being of the order of length, which is much larger than the order of h, which is the thickness, height, and the breadth or b, it can be shown that even with large displacements, large rotations, because the numerator and the denominator of your derivative definition is such that the denominator is also large because of the delta x1 that is involved, you would see that the strains are still small. So what is the advantage of that kind of a situation? Where you can utilize material linearity. In other words, your stress-strain relationship can be linear even with large displacements and rotations, but you will have your strain displacement relations, your kinematics will be non-linear because the displacement is large. So that large displacement and rotation makes it a geometrically nonlinear problem, but a materially or physically linear problem. So again, you have a way of nonlinear domain decomposition. Now we are not talking of domains which are spatial domains. We are talking of an abstract domain which is the mathematics involved. So there are certain aspects involved with the geometry which I have to consider nonlinear, certain aspects involved with the material which I can consider linear at least up to a certain level, and then I have to bring both of these two together. So that's how we try to include nonlinearity in an ingenious way instead of forcing that nonlinear model on anything and everything. It might be an overkill. You might be unnecessarily involving too much more computational resources than you actually need. So it's very important that you go for the rigorous physics, the state-of-the-art math, but at the same time, make sure that you don't apply it everywhere. You apply it only where it is really needed. So then you still keep your model size within the limits that are required. So I think we have looked at that. So yeah, let's go to the next one, which we are talking of as no body moments. So already we have, so from these two, we have ended up with your sigma ij is equal toCijkl into gamma kl, where C's are constants. Now, we said that there are 3 into 3, 9 components over here, 3 into 3, 9 components over here. But we know by the very definition of the strain itself, there are many, many different definitions of strain, but many of them, many such definitions are such that it's symmetric. In other words, your transverse or shear strains, or rather all shear strains, are such that your gamma KL is equal to gamma LK. In other words, interchanging these two subscripts or indices doesn't make any change. So because of the fact that interchanging K and L in gamma doesn't make a difference, the same K and L are appearing over here, and therefore interchanging over here also does not make a difference. So at this stage of elastic material and material linearity, we actually had 9 into 9, 81 constants, but here, because of this symmetry that you had only 3 normal strains and 3 shear strains. The other 3 shear strains were the same as the set that you took account of. So you would have actually, instead of 9, only 6. So in other words, you would have had 54 to start with. Now when you come and make the no body moment assumption, there's no, just like body forces, which is essentially your gravity, etc. We discussed this before. There could be a possibility of dipole moment, etc. distribution and a magnetic field that the material is placed in. Therefore, there could be moments which are within the volume of the body or the material. So which means that you would not have your sigma ij equal to sigma ji. But luckily, most of the materials that we deal with and the kind of fields that they are exposed to for most of their application is such that there are no body moments, or at least if it is there, it is negligible in terms of its effects compared to the mechanical stresses and the other things that come, like inertia forces, etc. So you would be typically able to neglect that, which means that just like what you did with K and L interchange, it is called a minor symmetry, because a major symmetry would involve the first 2 aspects of this same as the second 2. In other words, I and J together equal to K and L respectively. So that we are not yet gone to. So what we are looking at is right now what is a minor symmetry, and the first minor symmetry is purely by the definition of the strain. So very fact that you're defining many kinds of strains as symmetric means that it has reduced from what it was earlier, 81, it has reduced to 54. Now you're bringing in this no body moment. Once this comes in, your I and J can be interchanged. In other words, the shear stresses are complementary for the moment equilibrium that you could have in such materials, and therefore this is also reducing instead of 9 to 6. So both stresses and strains have reduced to 6, and therefore you end up with, from 54, you drop down to 36 now. So 6 into 6, 36 is what you end up with. Now, in reality, you actually have to deal with these indices the way they are if you want to be mathematically rigorous, because this is how these quantities are in reality. They are neither scalars nor are they vectors. They are second order tensors, these two. And because this is a quantity which relates to second order tensors, this becomes a fourth order tensor, and that's why it's having 4 subscripts over here in a particular representation, in a particular reference set of reference frames that you would have chosen. If you choose different reference frames which are aligned differently with that, your C values will change. Similarly, your gamma and sigma values will change, but the equation in its form remains the same. So if you would want to write this in a purely tensorial notation, you would write it as sigma double underline C with the 4 underlines and your gamma that you have with 2 underlines, and you would be contracting it twice because you're essentially trying to get it internally multiplied in 2 ways. So this you can think of as an extension of your dot product for vectors, where you know that 2 vectors become a scalar. Here 2 tensors, one of them being a larger order tensor, the 4th order tensor. Once this dot product happens, the double dot product essentially becomes your sigma. So again, I'm not bringing all of these in a very rigorous sense. It's just to give you a glimpse of what typically is done in these kinds of situations. There are other courses where we will be looking at these in a little more mathematically rigorous way. So what is important for us is that instead of dealing with what we started off with 81 constants, by very definition it dropped to 54. By the fact that most we are dealing with do not have body moment distributions, we would have only 36 now. And instead of dealing with 2 indices, I can now write it just as a vector of sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6. Out of the 9 stress components, only 6 are independent, and therefore I need to only deal with them, and instead of dealing with a 3 by 3 matrix earlier, now I deal with a 6 by 1 column matrix, or a column vector if you want to call it, right? So what these correspond to is that this is nothing but your sigma 1 1, this is your sigma 2 2, this is your sigma 3 3, and here a convention is used that in the first shear you drop off 1. So in other words, only 2 and 3 are left. Okay, and then you go on cyclically 3 1 and 1 2. Of course, you can interchange these in certain things. Certain textbooks and references, you will see that these are jumbled up, but this is a way in which a lot of the tensorial equations and notations can be simplified. In particular, in the composite literature, this sixth element, which is associated with the in-plane 1 2, is very, very important. If one is associated with the longitudinal direction, that is along the fiber, and the transverse direction is associated with either 2 or 3, then you would see that this is an important stress that needs to be accounted for, and you will usually have only sigma 1, sigma 2 and sigma 6. We will look at that once we get on to one of the future assumptions that you're going to make in this particular list. So we will revisit that. But right now, it's important for you to understand that in reality, this is a second order tensor, but for purely mathematical manipulation purposes and for our own simplicity of derivation, we are putting its measure numbers in a column matrix, the independent measure numbers only, and then we are having, instead of a 3 by 3 matrix, we are having a 6 by 1 column vector representation of that. The same thing we will do with the strain as well. So all that I have to do is to just replace your sigmas with gamma on both these sides, and that's essentially what you're having, that because of the fact that you have, by the very definition of strain, gamma KL equal to gamma LK, therefore the gammas are also can be written together, their measure numbers can be put down as a column matrix, and then this is what we mean by that. Therefore, now when you're relating the sigma 1, sigma 2, sigma 3 all the way to sigma 6 to gamma 1, gamma 2 all the way to gamma 6, your C, instead of having 4 indices there, I can do with just 2 indices over there. So in other words, I will write my sigma I is equal to Cij into a gamma j, right? Here, of course, I have to very specifically mention that my I and j are running between 1, 2 all the way up to 6, not only up to 3, because that is our typical convention that we have for Latin indices, that when we don't mention it, that means that I and j or k and l, whatever it is, will run between 1, 2 and 3 only. But now it runs all the way up to 6. All these 6 elements are involved over here, and this is the 36 that we are talking about in this particular case. Now, so far we have not mentioned anything about the overall symmetry of this 6. What we talked about only is in terms of what I mentioned as minor symmetries. So because of I and j being equal, these two can be interchanged as well. But both of these simplifications that we have are essentially minor symmetries, because they are not happening at the center of your fourth order tensor. It's happening between your first and second index or the third and fourth index. So these are your minor symmetries. Now we will look at a major symmetry with the fourth approximation that we are going to make. So any doubts about it so far? First three? Okay. So let's go to the next one, which is the existence of the strain energy density. Okay. Now SED is an abbreviation we'll commonly use to refer to the fact that there is a certain way in which the material is going to store the energy based on the work that is done because of the external loads that are acting on the body. So you have any arbitrary body. It could be a beam, it could be a shell, it could be a three-dimensional body where there is no distinction between the different dimensions in the 3D space. So whatever that is, essentially you are going to have certain boundary conditions which are going to be certain geometric boundary conditions that are going to be associated with it. There are going to be certain loading boundary conditions that are going to be associated with it. There could be distributed loads that are acting somewhere. There could be a shear kind of a distribution that is going to be acting somewhere. Whatever you are having over there, these are all external loads that are coming in, and those external loads are going to make this body, which is not a rigid body, it's an elastic body, it could be any flexible body for that matter. Essentially, it is undergoing certain stretching, it could go straining in different directions, so both normal as well as shear, and all of that means that there's a capability to store certain energy, and that energy is distributed throughout. So if you take a small infinitesimal volume element over there, you see what is the amount of energy that is there over there. So you can divide that energy U by that volume V, which is what we talk of as the strain energy density. So essentially, it's very similar to your potential energy. So if you throw up a ball, you know that you're giving a certain kinetic energy. The kinetic energy is reducing as it goes to its topmost point that it can and then falls off. At the topmost point, it's having a lot of potential energy. So that potential energy, that is a rigid body that you're dealing with as a model. But here what we're talking about is the model itself. When you're applying these forces, instead of moving, which also it could do, it could be a combination of both. In fact, in flight vehicle structures, you will have both of these occurring simultaneously, and that's why your flight and space mechanics course and this flight vehicle structures course, though taught independently by different instructors, eventually is something that you have to stitch it together, because you cannot, there you're dealing with rigid body dynamics. So you're dealing with all the elements of the aircraft which are not deforming themselves. So all that energy that is being given because of the propulsion system that you have, or any maneuvers that you're doing because of the control surface deflections, etc. It's all in terms of the overall motion of the aircraft, in terms of its pitching, its rolling, its yawing, and various other accelerated motions in the translational sense also. But in addition to that, there is some flexibility of all the structural elements, and that is also happening simultaneously, and some energy is going into all of them as well. And here we are trying to deal with those two separately, but eventually you will have to look at both of them simultaneously. So now this fact that there is a strain energy density means that there is a certain way of storing that potential energy until you are releasing those loads. So once I relax these loads, as long as we have assumed that it is an elastic material, we know that after unloading it comes back to its original shape. In other words, whatever work that you had done, it was stored as strain energy, and once you remove that, it's being basically getting released, and whatever deformation it had, it's being reversed. So now this strain energy density, we already defined it as the energy that is stored per unit volume. So that's in the limit, because this is essentially, you will talk of as a delta U, capital delta U by delta V, where this is this delta V element that you're talking about, and you will take the limit as delta V tends to 0, right? So which is what you define as that partial derivative of dou U by dou V, and that is what is defined as your strain energy density. And we will refer to this as U3D, the fact that it is an energy per unit volume, because very soon when we are going to be dealing with beams, we will talk of a quantity called U1D, which is the energy stored per unit length of the beam. And similarly, when we are dealing with plates and shells, we will talk of an U2D, which is the energy stored per unit area or surface area of the beam's reference, plates reference plane, or the shell's reference surface. So this will have the units in SI of joules per meter. This will have the units of joules per meter squared, whereas what we are interested in right now on this slide is only this, which is joules per meter cube, which is a volumetric density of the strain energy that is of interest to us. Now, the fact that this exists for these kinds of materials means that you have this dou U by dou V. First of all, you already have your, from the previous assumptions that you have made, you have shown that your particular stress that is involved is given by your stiffness multiplied by your Okay, so you have this. Now, you know that if you plot your stress versus strain, this particular element, let's say, is sigma I, where I is fixed number, either 1, 2, 3, 4, 5, or 6, and the corresponding gamma I you're trying to plot, you would see that you would have a, in the linear case, this is what you would have, and this area under this is what is your U3D. Okay, so you can also have what is known as a complementary strain energy, and you could see that in a linear problem, both are numerically equal to each other. That this area that you have over here, if I call it as, let's say, U bar 3D, numerically speaking, these two are equal to each other. But the definition is very different for each of them. Your U3D is defined as an integral of your sigma I d gamma I. And of course, there's an implied summation. There's also not only an integral there, but also a summation from I equal to 1 to 6 that is involved over there. So now that is what you're trying to deal with. And of course, it also has to be integrated eventually over the volume if you want to get the total volume. But what you're talking about is a density over here, and therefore that volume integral is not there. It's only an integral with respect to the strain, which is gradually increased from a 0 value to a particular numerical value, and you're talking of this. This, of course, if you go all the way up to failure strain, then you have what is known as the property of the material called the fracture toughness in that particular direction, or associated with that particular mode of stress and strain that you're talking about. In reality, of course, we are summing over all of them, and so you would be including all of that together. Now we can substitute your constitutive law, which is, we call this stress-strain relationship as a constitutive law, essentially a material property. So once you substitute that there, you would see that you have Cij gamma j, and then you would have a, because of d gamma I, you can integrate that, you get a square out of that, and so you see that you would have a gamma I gamma j. But now, if you can take the derivative of this, that is your dou. This is one more way of defining your stiffness, that it's that's what you've been always talking about, right? As far as you have a linear portion of this particular curve, the slope of that curve is your Young's modulus, even in your isotropic materials. So same thing, you're talking of an equivalent Young's modulus associated with a particular combination of your one of the 6 stresses with one of the 6 strains. So that particular stiffness element is nothing but your derivative of your sigma I with respect to gamma j. It just happens that sigma I is linear in this case, so if you just substitute Cij gamma j, the derivative with respect to gamma j will go, and you will get Cij equal to Cij over here. So now, the fact that your strain energy exists means that you are having a further level of your U3D. So that U3D that you talked about is your integration from sigma I over your d gamma that you have over here, right? And that is energy per unit volume, but it is a property of a particular point. So when you're talking of this infinitesimal volume, you're talking of a particular point over there. You're constructing a small infinitesimal volume of delta x, delta y, delta z around that, and then you're taking this particular limit as your delta v tends to 0, then that's when you end up with your U3D as this particular definition. Now, we will use this particular fact that we have strain energy density defined in the next class to show that what we had up to this point, we had 36 constants. We are going to be able to reduce that further, because now we will take advantage of the fact of a major symmetry in that I and j can be interchanged. Or in other words, in your originalCijkl, what we are saying is that this is the actual mathematically rigorous thing that we're talking about. These two can be interchanged, and you would have the same value for your C. Okay. Why is that true? Because of the existence of strain energy density is just a few steps ahead of this, which we will do in Monday's class. So we will take it forward from that. So once that happens, very clear to see that instead of the 36 constants that you have, you still have 6 by 6 matrix, but it's a symmetric matrix that you will end up because I and j are equal to each other. So therefore, you have 6 diagonal elements. So if you in the 36, if you remove the 6 diagonal elements, you end up with 30 off diagonal elements. Now the off diagonal elements are the corresponding pairs are equal to each other in a symmetric matrix. So all that you have is the number of off diagonal elements are 15. So you have the number of diagonal elements are 6. So 6 plus 15, you will have 21 elements that are left. Okay. Now, why is that case? Why does the existence of U3D lead to this? We will see at the beginning of next class. Thank you. Any questions? Okay. Thank you.